For this next topic, we're going to talk about angular kinetics. So a lot of the same components that we discussed in linear kinetics will also transfer to this topic, just in a little bit different form. So we're going to talk about moment of inertia relative to angular motion and how that might change, again, relative to angular motion. We will talk about Newton's first, second, and third laws of motion as they are applied to angular motion. And then we will also discuss angular impulse momentum and the relationship between these components. So angular inertia is going to contain a lot of the same concepts similar to linear kinetics. So inertia is still the resistance of a body to changing motion. However, angular inertia is the property of an object to resist changes in angular motion. So it's unlike linear inertia in that it's not solely dependent on an object's mass. Moment of inertia quantifies how an object's mass is distributed relative to a specific axis of rotation. So a mass further from the axis creates more angular resistance, while a mass closer to axis creates less angular resistance. So if you think about our torque equals force times moment arm situation relative to this, it's pretty similar in that a longer moment arm is going to cause or allow for more torque if force remains the same, while a smaller moment arm is going to render a lower amount of torque if force remains the same. So if you try to think about it that way, that might be easier, but this is an important concept to remember in that mass distance from an axis of rotation is going to have a large effect on angular resistance. So the moment of inertia in angular motion does consider each individual mass particle as its own. So mathematically, moment of inertia can be defined as I equals the sum of m times r, where I is the moment of inertia about an axis A through the center of gravity, equal to the sum of the mass of the particle I in kilograms times the radius from particle I to the axis of rotation A in meters squared. So that squared component is going to be very important when you're working on your calculations and your problem set. Another approach to defining and calculating moment of inertia in angular motion is using what's called the radius of gyration. So this is more of a simpler approach to considering mass distribution, but all in all, it describes how far from an axis of rotation all of an object's mass must be concentrated to create the same resistance to change in angular motion as the object had in its original shape. So the radius of gyration makes it easier to calculate inertia. So we can mathematically define it as I is equal to mk squared, where I is the moment of inertia about an axis A through the center of gravity of that object, is equal to m, which is the mass of the object in kilograms, times the radius of gyration about an axis A through center of gravity in meters, and again this k is squared. So given these mathematical formulas, in calculating moment of inertia, we can see that it is dependent upon one, an object's mass, and two, the distribution of that mass. So distribution actually has a greater effect compared to mass because this k, or the distribution of the mass, is squared. So mathematically, if you double the mass, you're going to double the inertia. So if you take this times 2 then that would render I times 2. However, if you take the radius of gyration or the distribution of that mass and multiply it, then you are going to get I quadrupled. Okay, so if you took K times 2, that's going to render a larger effect with the object's moment of inertia. So conceptually, we can know that the distribution of an object's mass is much more impactful on the object's moment of inertia. Something that's important to note with angular motion, though, is that not all rotation occurs around an object's center of gravity. So our eccentric axis is an implement axis not passing through the center of gravity. So if you think about someone holding a bat or a racket or a hammer, where you are holding that implement is going to be considered the axis of rotation, but that's not the object's center of gravity. So this new axis would be called the parallel axis. And in this instance, I, or the moment of inertia, is going to be greater if the largest component of mass is distributed further away from the axis of rotation or further away from you holding that implement. Mathematically defining moment of inertia about an eccentric axis looks a little bit different because you're going to take the moment of inertia about an axis B or about that eccentric axis, and you're going to equal that to the moment of inertia about the axis through the object's center of gravity, and which is also going to be parallel to axis B, plus the mass of the object times the radius or the distance from axis B to the parallel axis through the center of gravity, and of course that radius is going to be squared. So in discussing moment of inertia specific to angular motion in the human body, we have to first kind of go over the three principal axes in the body, because obviously this is where rotation is going to primarily occur. First one is the anterior posterior axis. This is going to go from your anterior portion of your body to your posterior portion, or front to back. If you think about doing a cartwheel, that's when full body motion, you would be relatively rotating around that anterior posterior axis. Transverse axis, if you think about doing a somersault, this is where you have an axis going from right to left or left to right. So if you envision doing a somersault, you would be rotating relatively about this global transverse axis. Longitudinal axis, or also known as the polar axis, is from top to bottom or bottom to top. So if you envision yourself doing a twist, this would be about the longitudinal axis. So the moment of inertia around each axis depends on the position or the orientation of the limbs relative to these axes. So if you think about how far or how close your segments are to a given axis, or whether you have your arm flexed or extended, those types of things are going to influence this moment of inertia around a specific axis and relative to our human body orientation. So again, here is a good depiction and review for the three axes. The longitudinal is from top to bottom. Transverse axis is going to be left to right. Okay, and then anterior posterior is going to be front to back. So there are a couple of ways that we can manipulate moment of inertia within the human body, and one is altering the relative angle at a joint or joints. This changes the moment of inertia by changing the mass distribution around a joint axis. So if we change the relative angle at a joint, meaning we change, the segment, flexion, extension, if this is the elbow, the flexion or extension of the elbow, that is changing the relative angle at a joint. So if we do this through this range of motion, we will alter the mass distribution about a given joint axis here, which will change the moment of inertia of that particular joint. So a couple of examples of this: sprinter's leg during a recovery phase, or swinging a tool. Okay, if you say you're swinging a hammer, if you chuck up on the hammer, you will reduce the moment of inertia of that object, because you'll by and large be reducing the radius between the axis of rotation and where the mass is mainly distributed. The sprinter's leg we will talk about in a couple of slides, so I'm going to save that component for that time. So we can also alter the relative angle at many joints, which changes the moment of inertia about our center of gravity by changing the mass distribution around the center of gravity. So if you think about figure skaters, when they are completing a spin, they will most of the time pull their arms very close into their body to reduce that moment of inertia that is rotating about the center of gravity or center of mass. And the reason for that is when you reduce that moment of inertia, you're reducing your body's ability to resist change, meaning that they're going to continue spinning at that velocity that they've established in a longer amount of time, rather than slowing down due to some type of resistance, mostly by having their arms away from their body, or their arms that are moving, changing their center of gravity location, and then thereby increasing their moment of inertia. Another thing, tuck versus layout position of divers and gymnasts in somersaults. You'll see divers, especially, and gymnasts, when they are trying to achieve a really high number of rotations in the air, they tend to tuck their bodies in. This is going to reduce their moment of inertia, meaning they're going to be less likely to slow down in the air, and more likely to achieve the amount of rotations that they're trying to, in order to succeed in the actual dive, or the move, or the somersault that they are trying to do as a gymnast. So with this knee and hip flexion of the recovery leg of the runner, the more that this knee is flexed, right, this is going to reduce the moment of inertia about the knee, thereby making the hip then flex, reducing the moment of inertia about that joint, and by and large you will be able to achieve ground contact with this foot much quicker again. So basically, if you reduce your moment of inertia during or with that recovery leg as quickly as you can, that is going to allow you to essentially have more turnover, right? So your contact time of this foot on the ground is going to reduce, and thereby reduce the other, so that you will ultimately be running at a faster pace. So what's interesting though is that with moment of inertia relative to angular motion and linear velocity, there is this trade-off that is experienced, because we know that tangential velocity is greater with a longer radius, but moment of inertia is greater also with a longer radius, meaning that our body's resistance to change is going to be greater, meaning that it's going to slow down, or things are going to be harder. So if you think about swinging an implement, especially, you have a trade-off between ease of swing versus effectiveness of velocity achieved. So if you have a longer bat or a longer golf club, you will achieve a greater tangential velocity of that club head or that bat, but is actually going to be harder to swing these implements. And a lot of that is more relative to the mass being distributed further away from the axis of rotation. So we have these technique changes that we use, especially in softball, baseball, golf, where we can choke up on a certain implement, gives us a little bit more control, a little bit more stability, but those using that technique specifically is not going to increase the linear velocity of that implement itself. So one thing that's interesting specifically with golf is how they have changed club head design to kind of give, especially amateur and leisure golfers, a little bit more of an advantage with the game. Is instead of having this solid mass club head, they've actually reduced the amount of mass that is distributed in the club head, meaning that this will reduce the moment of inertia overall, because it will ease the complexity or the strength that it takes to essentially swing the club. So this is all we have for the first part of angular kinetics, and I will upload the second part on in a couple days.